In this video I'm going to talk about a topic that's extremely important for printed circuit board design, and especially the higher the frequency you go to, the more important it is. And this is power supply decoupling. And what do I mean by power supply decoupling? Well, I mean trying to turn your power source, power supply, locally for the IC of interest into an ideal power supply. This is our power supply here, and here I've drawn a 5-volt power supply, and I've got two loads connected to it, load 1 and load 2. And a load could be anything like an amplifier, it can be an IC, it can be a logic gate, it can be a microprocessor or microcontroller, anything like that, anything that will draw current at transitions between digital states. But what is an ideal power supply? Well, first of all, an ideal power supply delivers a constant DC voltage to the load. So there would be a constant 5 volts here and a constant 5 volts here, and you need to make sure that's the case. Second, it doesn't allow the propagation of AC noise from the load back on the line. So let's say this guy is transitioning from high to low, and it's drawing current or pushing current back out on the line. You want to make sure that that current doesn't get injected over here to this load and affect it. The third consideration is you want a 0 ohm AC impedance between power and ground, between here and here. You just want DC to be held at 5 volts, but any other frequency above that to just see a short between the high level and ground, because if it doesn't, it can sit up there and maybe create some very higher frequency oscillations in the 5 volts or in the ground plane, and that would happen maybe because like this one over here, the currents are getting injected in or out of the circuit. So the technique of power supply decoupling is to make the source look like an ideal source, and the easiest way to do that is to just add capacitors into your system. Let me change my color. You will add a bulk capacitor here, bulk, near the source. You'll add local decoupling capacitors here. So these are local decoupling capacitors, and maybe there's another one over here. And just to give you a sense of the values, this one may be 10 microfarads, and this one is 0.1 microfarads, 0.1 microfarads, and I'll go into the choice of those values a little later. But the big idea is that these capacitors will make that power supply look ideal. Now let me walk through the two different but related goals that these capacitors serve, and that will indicate why they allow the power supply to look like an ideal power supply. The two connected, related goals, but distinct goals that these capacitors serve is: one, they allow for a local charge supply, a reservoir, and two, they allow for filtering. Now, what do I mean by charge supply? The capacitors can act as a local charge reservoir to provide the charge that these circuits need during their transitions. Like, let's say that this power supply, it can only keep up with oscillations on the order of maybe a megahertz or even 100 kilohertz or something like that. Well, that's not going to be fast enough to power a circuit that's operating at 10 megahertz. And when that transition, it's going to pull a lot of current into it and maybe drag down this 5-volt line, which will then affect circuits further on down the line. So what you do, first of all, is you have this bulk capacitor here, a big Mondo 10 microfarad capacitor, which by Q equals CV, since this is a large capacitance for a given voltage, it's going to have a large charge. So when these circuits transition, they don't necessarily have to go all the way back to the power supply to do to provide the carriers for their transition. They can either look locally, so the local decoupling capacitor, maybe they can go back to the bulk decoupling capacitor and have enough charge to make that transition. And by using these large reservoirs of charge, they don't necessarily drag down the line or create a lot of high frequency oscillations on the line that can then affect other circuits. The second reason for including the decoupling capacitors is this filtering mechanism. So at the impedance of a capacitor, Z sub C equals 1 over J omega C. And at non-zero frequencies, this impedance will be finite. It'll be something less than infinity. And so as these loads transition at some frequency, let's say 10 megahertz, if these capacitors are sized appropriately, a lot of that noise from that transition will just be shunted to ground. It will just go to ground instead of traveling down the line and affecting other loads on the circuit. And that's one of the big reasons for having the local decoupling capacitor is for that filtering mechanism. But remember, both the bulk and the local decoupling capacitor serve both functions, both as charge supply, as a reservoir, and for filtering. Getting a few too many colors here, but I just want to emphasize for digital systems, these two capacitors are fine, the bulk and the local capacitor, local decoupling capacitors or capacitors. There'll be many of the bulk and a few of the locals. But for very sensitive analog circuits, you may want to do something a little different. And let me scroll down and draw what that is. For a very sensitive circuit, I've drawn here, so let's say this is an analog circuit, and we want to keep it to a very, very quiet voltage source. We want to pull out all the stops. Well, the first two things are we include the bulk and the local decoupling capacitor, but the other thing we do is we may include an inductor here in between the two. And usually instead of an inductor in a circuit, you'll use a ferrite bead, but they serve the same purpose. They are an inductance. And what this does is not only are high-frequency circuits shunted to ground if they make it into the realm of the analog circuit, but also they may not get in there anyway because this impedance here is j omega L, so as the frequency goes up, the impedance goes up, and less of that signal can make it through from one terminal to another. This configuration is called the pi topology. And you can see it looks like a symbol for pi, and let me draw that out. There's the top hat, and there's one leg, and then there's the other leg, and that's this. This is a very effective circuit when you want to pull out all the stops and make sure you have a very quiet voltage to your analog load, or digital load for that matter. Now, something to be mindful of is that if you're going to use this topology, you should never, ever, ever omit these local decoupling capacitors, because to power the transitions here, it's going to have to go back. If this is omitted, it's going to have to go back through this inductor and pull its charge from the power supply and the bulk capacitors. And you don't want that because you've sized this ferrite bead, this inductance, so that it blocks high frequency components, and so it's not going to be able to operate appropriately.